Okay, so today what I wanted to do was to prove the Hansen-Wright inequality. Right, so we use that on Monday to prove the distributional JL lemma. Once we're done with that, we're going to move into norm estimation for other norms. So LP norm estimation for P not equal to 2. Specifically, we'll look at the case where 0 is less than P is less than 2. If it's less than 1, it's not a norm, but it's still a well-defined function of the vector, and we'll show that you can do that in low space as well. And then we'll wrap up by talking about pseudorandom generators for space-bounded computation. Right, so we've found ourselves numerous times in a situation where if only we had a perfectly random hash function, our analysis would be simpler. But then, we can't afford to store such a thing, so we talk about how to de-randomize it. Maybe I'll use 2-wise independence or 4-wise independence or log n-wise independence, or maybe, well, that's all we've seen so far is basically using k-wise independence. But there are other tools in the pseudo-random toolbox. Okay, so k-wise independence is not the only one. There are things like epsilon bias spaces, for example, and other PRG, other pseudo-random generators. So today what I want to tell you about is pseudo-random generators for just generic space-bounded computation, right? So if you have an algorithm that uses small space, there's just a generic method to generate pseudo-random bits that fools the behavior of that algorithm. Okay, and the first application of such kind of generic tools to streaming algorithms was for LP norm estimation when P is not 2. Since that paper, we've discovered that, in fact, you can actually solve that problem just using k-wise independence. So you didn't need this more generic tool, but it is a good general tool to keep in mind for other problems as well. Okay. So we're going to prove Hansen-Wright first. That's number 1. I've reminded you what Hansen-Wright is from the Monday lecture. So it's a tail bound for quadratic forms when the random variables are plus minus 1. So you have sigma 1 up to sigma capital N. They're ID plus uniform plus minus 1. You have a matrix A, which is square. What's the probability that sigma transpose A sigma deviates from its expectation by more than lambda? It's something that depends on the Frobenius and operator norms. I defined Frobenius and operator norms last time. I just wanted to thank Yeshwant, who pointed out to me over email that something I said for operator norm wasn't quite right. I said, well, first of all, what is the operator norm? Right, the actual definition of the operator norm is defined to be the sup over all x of ax L2 norm divided by the norm of x. Okay. Now, it turns out using linear algebra, there are other characterizations that are equivalent. You could also say it's the sup over all xy of unit norm, they're all L2 norms of just x transpose ay. One of the things I said in lecture was if it's diagonalizable, if A is diagonalizable, it's just the magnitude of its eigenvalue. So that's not, so that was the verbal bug I made. That's not always true. It is true if A is a real symmetric matrix, right? Then it's diagonalizable by an orthogonal matrix, then it's true that it's the magnitude of the largest eigenvalue. But just being diagonalizable is not enough. In our examples, if you remember, when we applied Hansen-Wright to proving the distributional JL lemma, our matrix A was of the form kind of B transpose B for some other matrix B. If you remember, our B looked sort of like Z transpose, Z transpose, Z transpose, and then zeros everywhere else and a 1 over root m, I guess. This was our B, and then our A was B transpose B. Right? When we applied Hansen-Wright on Monday, so this matrix is in fact a real symmetric matrix. So it is by the spectral theorem and diagonalizable by an orthogonal matrix. So in fact, for this case, the operator norm is the magnitude of the largest eigenvalue. But that's not always going to be the operator norm if you don't have a, let's say, real symmetric matrix necessarily. Okay. So anywho, now I stated it Hansen right on Monday as this tail bound. For all lambda, there's some tail. It's a mixture of a Gaussian tail and an exponential tail, right? So Gaussian, like this e to the minus lambda squared is how a Gaussian behaves. It's how a Gaussian decays. E to the minus lambda is how an exponential random variable decays. So it's like, the tail bound again is the sum of the two, which is basically the same as the max of the two up to a factor of 2. So you decay like a Gaussian up to a certain point, but then beyond you don't get as good decay as Gaussian decay, you only start getting exponential decay. Okay. Now, tail bounds and moment bounds are equivalent. I'll say a little bit, I don't want to get too into the math, but I already put all of this in the lecture notes in the probability review. I uploaded it either last night or this morning. Whenever you have a tail bound that looks like this, like you say that some random variable decays like a Gaussian, that's equivalent to saying the moments of the random variable grow in a certain way. It's equivalent in both directions, right? So the moment inequality implies the tail bound implies the moment inequality. When you say that your tail bound decays like the max of a Gaussian and an exponential, that similarly implies a bound on all the moments, okay? So maybe I'll just say a little bit about that without spending too much time on it. But remember, okay, so if you haven't seen this before, you can define a norm on random variables. So that's this p norm here that I'm highlighting in yellow. Okay, so the p norm of z is just some real valued random variable. The p norm is the pth moment, z to the p, and then you take that pth moment and you take the 1 over pth power. Okay. And you can prove that for any p that's at least 1, this is a norm. It satisfies triangle inequality. It is a norm. It's a valid norm. Okay, that's the fact that it's a norm is something called Minkowski's inequality. If you haven't seen it before, it's a norm for p greater than 1, for p at least 1. Okay. So so I'm saying that this kind of tail bound is equivalent to bounding all the p norms of the random variable. Okay, why is that? Okay, so again, let me just give you a little. Let's say that probability. Let's just do it for Gaussian. Let's say that probability that z is greater than lambda is at most, this less than trivial means up to a constant factor, is at most e to the minus some constant lambda squared over alpha squared. Let's say that someone told you that. I claim that implies a bound on the p norms. Why? Because this implies that, the expectation, what is the expectation of z to the p? That's equal to the integral from 0 to infinity of p times x to the p minus 1 times the probability that z is greater than x dx. Okay, right. This is the pth moment. If you haven't seen this, it follows from integration by parts. The normal way you define the pth moment is you say it's the integral of x to the p times the PDF, right? Some PDF of x dx. This PDF is the PDF of the absolute value of z. But you can show via integration by parts that the two integrals are actually equal. Okay. So then now, you told me that I have a bound on the probability that z is bigger than lambda. So I'll just apply that bound to this, okay? And then I get that this thing is at most some constant times e to the minus c lambda squared over alpha squared. And now what am I integrating? I'm integrating exactly the Gaussian tail bound. Like this is exactly the pth moment of a Gaussian, okay? And you can look it up. The pth Gaussian, the moments of a Gaussian are known, and it's exactly this is. You can prove that this is at most O of root p, alpha root p to the p. Okay. Just based on Gaussian moments. And similarly, the other direction, if you tell me that the expectation of, if you tell me that the pth moment is bounded by something, then we know that the probability that z is bigger than lambda is less than, well, it's equal to, let me write it's equal to the probability that z to the p is bigger than lambda to the p. But by Markov, that's less than b over lambda to the p. Right? This is Markov's inequality. And so if I tell you that b is something alpha root p to the p, if I tell you that this is something like O of alpha, let's just say, let's just get rid of the big O, it doesn't really change things. At most, let's say some constant times alpha root p to the p over lambda to the p. So if you know that's true, then what am I going to do? I'm going to just basically set p. I can, I have a bound on the pth moments for all p. So I'm allowed to freely choose p. So how am I going to choose p? Choose p, make the base of that exponential be, let's say, something like 1 over e. So I'm going to choose p. So let's say choose p to be something like lambda squared, or lambda over c alpha, e c alpha squared. Then this is equal to e to the minus p, which is e to the minus lambda squared over, e squared c squared alpha squared, which looks a lot like, right? So this exponent is basically the same exponent as what you have here, right? It's e to the minus some constant lambda squared over alpha is basically serving as the standard deviation, or alpha squared is like the variance for Gaussian. Okay, so I don't want to, so I'm not going to do all these calculations. You can look at the lecture notes if you want in the probability review section. But the punchline is proving a tail bound that holds like this is equivalent to proving bounds on all the moments or on all the p norms. Okay, so the way we're going to prove Hansen-Wright is to bound all the p norms. Okay, so that will be this equivalent to proving what I wanted to prove. So let's do it. Let's bound all the p norms. Okay. So before we do that, I'm going to teach you a technique called decoupling.
Did we show both directions of that equivalence?
Sorry, what? Say it again?
Did we show both directions of that equivalence?
I think so. So the directions are divided by this yellow line right here. Right? So above it, okay, I'm showing that if you have a tail bound, then you have a moment bound. And below it, I'm showing if you have a moment bound, then you have a tail bound. But again, look in the probability review notes. I have things more written in detail there. So just take it for granted that these two things are equivalent for now. And let's bound the p norms. Okay. So actually, before I do decoupling, let me actually do one simple thing before that. I'm going to reference a theorem that I think I've already put in the probability review a while ago, which is called Khinchin's inequality, which says that if sigma 1, sigma n are IID plus minus 1, and let's say x is a fixed vector, then if you look at the p norms of sigma dot x, so this is the same thing as, right, sum of sigma I xi. This is at most root p times the L2 norm of x. Okay. And kind of why is that true? Well, let's just prove it in the case that, let's say, p is an even integer. Then if you look at expectation of the sum of sigma I xi absolute value to the p, then that's the same as the expectation of the sum of sigma I xi to the p without the absolute value, because p is an even integer, right? So raising to the p is definitely going to be positive or non-negative. And then you can expand this thing out, right? So this is equal to the sum of I1 up to IP, xi1 up to xip, and then the expectation of that product, sigma I1, sigma IP. Okay. And now the thing to note is, some of these indices I1 up to IP might be repetitive. All those P indices are not necessarily distinct. Okay, so let's just write this as like a sum over all kind of monomials of x to some index, let's call it J1, raised to some power D1, xjr up to some power dr, times the expectation of sigma J1 D1 up to sigma JR dr. Does that make sense? Where like here now, the JTs are distinct. The JTs are distinct. So I grouped I's that were the same.
So D1 plus ... dr is equal to P, right?
That's right. Plus dr is equal to P. Okay. Right. So now the thing to observe is, what is the x? So first of all, by independence, this thing is the product over T of the expectation of sigma JT to the DT. So what is this what is this product? Well, there are only two cases. In one case, all the DTs are even, and then sigma to the D is 1, and then the product of 1 a bunch of times is 1. So this thing could be 1. On the other hand, even if a single DT is odd, then sigma to the D is going to be the same as sigma, and the expectation of sigma is 0, right? This is a plus minus 1 random variable. So this is either 0 or 1. Either 0 or 1. Okay. And what if sigma had not been sigma? What if sigma had actually been a Gaussian G versus, let's say, it had been sum of GI xi, where the GIs are ID Gaussians? Then you could do the same kind of expansion. You'd have a similar story. It would either be 0 if any Gaussian is raised to an odd power, or if all the Gaussians are raised to an even power, it would be at least 1. It might be more than 1, because like the expectation of a Gaussian squared is 1. I'm talking about a standard normal random variable with variance 1. So the expectation of GI squared is 1. The expectation of GI to the 4th is 3. I think the expectation of GI to the 6th is 5, or maybe 3 times 5 or something. But the point is, it's always at least 1 if you raise it to an even power. So this is term by term dominated by the Gaussian case. So this is at most that same sum of xj1 d1 blah 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 xjr dr of the expectation of the Gaussian case, which is gj1 d1 gjr dr. Right, and this is just the same thing as the expectation of the sum of gi xi raised to the p. So we've just proven, this is the inequality here. We've just proven that the Rademacher case has moments that are strictly bounded by the Gaussian case. And if you haven't seen this before, now I'm going to cite a fact about Gaussians. If you add independent Gaussians together, you get back a Gaussian whose variance is the sum of the variances of the Gaussians that you added. Okay, so gi xi is itself a Gaussian. It's a standard normal random variable with mean 0 and variance L2, xi squared, sorry. Okay, so this is the variance, this is the mean. So you're summing up you're summing up capital N Gaussians whose variances are each xi squared. So when you do that, you get back a Gaussian whose variance is the sum of the variances. So this is equal to basically the expectation of the L2 norm of x times just now some 1 Gaussian to the p. And then you can just look up, you can look up what is the pth moment of a Gaussian, and you'll get exactly what, you'll get something that is at most root p to the p. Okay. And if you then remember the p norm takes this whole thing to the 1/pth power, etc. So here you're going to take this all to the 1/pth power, and then you're going to get something like that's at most the L2 norm of x times the square root of p, which is exactly what I wanted to show. Okay. I think that the pth moment of a Gaussian, if p is an even integer, is something like there's an exact formula. It's like p over 2 factorial divided by 2 to the p, sorry, not p over 2 factorial. P factorial divided by 2 to the p over 2 times p over 2 factorial. There's whatever. You can look it up if you want. But the point is that this thing is, which I think is something like 1 times 3 times 5 times 7, whatever. I think you usually prove that by some repeated integration by parts. But you can, just take it as a given for the lecture. Okay, so good. So this is Khinchin's inequality, which is a linear form with Rademacher's, right? So it's sum of sigma ixi. We're interested in quadratic forms. Okay. So now let's see how we're going to do that. Hansen right is about quadratic forms. So you can view it as like a generalization of Khinchin to degree 2 polynomials instead of linear polynomials. So we're going to use a tool called decoupling. And here the theorem is that if you have the sum I not equal to j of aij sigma I sigma j, p norm, this is at most 4 times the sum I not equal to j of sigma of aij sigma I sigma j prime, p norm, okay, where sigma 1 up to sigma n and sigma 1 prime up to sigma n prime are 2n IID plus minus 1 variables. So basically I can replace kind of, so I mean, what is this, right? This is like basically sigma transpose a sigma minus the expectation of sigma transpose a sigma. Whereas what this is sigma transpose a sigma prime minus the expectation of sigma transpose a sigma prime. Is that, or not exactly, it's minus the diagonal, let's say. So I'm allowed to replace one of the sigmas with a sigma prime and pay at most a constant factor in my p norm. That's what decoupling says. Okay, good. So let's prove this. Oops, sorry. Okay. So proof. Let eta 1 up to eta n be like IID Bernoulli a half. So it's 0 with probability 1/2 and it's 1 with probability 1/2. So right, this implies that the expectation of like eta I is a half, right? So I can write this thing is equal to 4 times the times this, the expectation over eta, sum I not equal to j, aij. Is this what I want to? Yeah. Eta I kind of 1 minus eta j. Okay. Right, just because, I mean, I'm basically just in a convoluted way multiplying by a quarter on the inside of the norm, and then I'm multiplying by 4 on the outside of the norm. So I haven't really done anything. And then now what I'll do is I'll say that this is at most 4 times the this thing, some I, I'll basically pull the expectation over eta outside. So if you want me to be clear, I mean, this, sorry, I forgot to put the actual p's, I mean the sigmas. So here there's like sigma I, sigma j, and here there's also sigma I, sigma j. Okay. And, you know, remember I told you what the definition of the p norm is? Yeah, that's right. Yeah, so no, I think you got your question answered. I told you what the p norm is. It's like the expectation of blah raised to the pth power all to the 1 over p. So if you want me to be more clear, this is like the LP norm over the randomness of like sigma. And this is the, here you're taking the expectation over both eta and sigma. So, right, there's like an expectation over both eta and sigma of whatever to the p, all to the 1 over p. And this follows by Jensen's inequality. Okay, so Jensen basically says whenever you're taking, so let's say phi is a convex function, and you're looking at phi of the expectation of a random variable, that's at most expectation of phi of the random variable. So like basically whenever, so in this case, the convex function is like absolute value to the p. So Jensen says I can pull the expectation from inside the norm to outside. This is a common trick that we're going to use a lot, is basically pulling expectations inside the norm, outside the norm. Jensen lets you do that. And now what we're going to say is, look, what is an expectation? An expectation is just an average, right? So there must be a fixed choice of the eta. I mean, eta is just a 0, 1 vector, right? It's a random 0, 1 vector. But it is a 0, 1 vector. So look, this is the average. I'm saying that now what I want to say is that there must exist a fixed vector that achieves a value that's at most the average. There's always someone who's at most the average. So this is at most now 4 times sorry, I lose my train of thought. Yeah, so I guess what I want to say is there must be some fixed, okay, good. So not at most the average. I want to say that, so this is the average. There must be some fixed eta that's at least the average is what I want to say, not at most the average. So this is at most the sum I not equal to j of aij sigma I prime 1 minus eta j prime sigma I sigma j, where now the randomness is only over sigma, where eta prime is fixed. It's not random. Eta prime is some fixed vector. It's a fixed 0, 1 vector, right? So I'm saying that there must be some vector whose value is at least the average, okay? And then now I can just write, let's write this as 4 times the norm of the sum, let's say I in S, the sum J not in S of Aij sigma I sigma J, okay, LP norm, where here I just define S to be, I guess, the set of all I such that eta I prime is 1. Does that make sense? Because your eta I prime 1 minus eta j prime is going, that product is either going to be 1 or 0. It's going to be 1 if I is an S and j is not an S. Otherwise it's 0, so it doesn't appear, it doesn't matter. Okay. And now this is equal in distribution to 4 times this thing. Does that make sense, right? Because basically what I'm saying is, look, here's my vector sigma 1, sigma 2, sigma capital N. This is a vector of ID plus minus ones. And I'm saying, there's a set S, and then there's the complement of S here, right? And what I'm saying is, look, if I just replace everything in the complement of S with like sigma J prime up to sigma N prime, and this is now my new sign vector. This new sign vector is also just a vector of independent signs. It's equal in distribution to the previous vector. So replacing those J not in S with sigma J prime doesn't change the distribution of the random variable at all. It's not just that the norms are equal, the distributions are identical. Okay. And now I'm going to do something funny, which is I'm going to add 0 in a funny way. I'm going to say, look, this thing is equal to 4 times the norm of, let's say, the expectation over sigma not in S, sigma, let's say, projected to not in S, or sigma not in S, expectation of sigma prime in S, of the sum. Here, actually, I'm going to write here all ij, actually. I don't need to remove the diagonal. Of sum over all ij of aij sigma I sigma j prime. And then I'm going to do p norm. And then I'm going to do Jensen again and pull these expectations outside. And this is at most 4 times the p norm of all sum of aij sigma I sigma j prime. And that's exactly what I wanted to show. Right? This is exactly that. Okay, so that's decoupling. Questions about decoupling?
So I guess it didn't need to be a p norm, right? It could have been any convex function of this sum.
Yeah, that seems to be the case. I mean, maybe the 4 would be well, would the 4 be something else? Yeah, maybe.
Well, it should still be 4, right?
Right, yeah, I think that's, so yeah, it should be fine. Yeah, I think you can do it with other convex functions too. Any other questions? Okay, so now let's prove Hansen right. So Hansen right. Okay, so we're looking at the p norm of sigma transpose a sigma minus the expectation of sigma transpose a sigma. Now, one nice thing about plus minus ones is that, if you look at the diagonal terms of sigma transpose a sigma, it's basically just equal to the sum of the diagonals of A. It's the trace of A, right? Just because sigma I squared is 1 with probability 1, which cancels exactly with the expectation of sigma transpose a sigma. Okay, so this thing is the same thing as the sum of I not equal to j of aij sigma I sigma j. All I'm trying to say is that the diagonals cancel out completely. So we can apply decoupling, and decoupling says is at most up to a factor of 4. That twiddle means up to a constant factor of the p norm of sigma transpose a sigma prime. Okay, and then now what I want to do is I want to do Khinchin's inequality. Okay, so if I first just condition on sigma, let's say, or condition on sigma, and now sigma, I can think of sigma as a fixed vector, and first take the expectation over sigma prime, I can apply Khinchin's inequality, and Khinchin says that this is at most basically the p norm of a sigma prime. So take the L, so it's the L, so right, what is it? It's like, actually, let me do this a little more carefully. So normally this would be like, it's at most root p times the L2 norm of x, right? So this is at most root p times the L2 norm of A sigma prime. But the L2 norm of A sigma prime is a random variable. So I have something like this, P norm there. Okay, does that make sense?
These are different norms, right? This is a vector norm.
Yeah, sorry,
The
that's
P norm
right.
is the random variable norm.
The L2
Maybe it's
norm is a
better.
vector. Yeah.
Maybe it's better to say like LP or something for
Yeah,
the.
maybe that will be less confusing. So these are LP is like I'll use LP to mean the random variable norm, and the 2 there is like Euclidean norm. And if you look at what the definition of LP is, then right, this thing is basically, this thing here is like the expectation of A sigma prime L2 norm to the P all to the 1 over P, right? But that's also the same thing as, I'll write it as, okay, let me do a different color. That's the same thing as doing L2 norm squared to the P over 2 to the 2 over P all to the 1/2. Okay, that's just like playing with numbers. I haven't changed anything. They're equivalent. So all I'm saying is that this is the same thing as root P times A sigma prime L2 norm squared LP over 2 to the 1/2. Okay. And then a fact about P norms is that P less than Q implies LP is at most LQ. This also actually follows from Jensen's inequality, and I have the proof in the lecture notes. You can take a look. It's not a hard proof, but I'm not going to, let me not waste time in lecture doing it.
Do we need P to be at least 2 or something though? Because
yeah, you do need P to be at least 2. So let's do P is at least 2. Yeah, otherwise the P over 2 thing is not a norm. But yeah, so this thing is at most root P times A sigma prime L2 norm squared LP to the 1/2. And then what I'll do is I'll just add and subtract the same thing. So I'll add the expectation of A sigma prime L2 norm squared and also subtract the expectation. So let me add the expectation of that thing and subtract the expectation of that thing. Okay. And the expectation of, right, the expectation of the L2 norm squared, right? The expectation of A sigma prime L2 norm squared, that's the same thing as the expectation of sigma prime transpose A transpose A sigma prime, which is just the trace of A transpose A, which is just the Frobenius norm squared of A, right? So I can do a triangle inequality and pull out a Frobenius norm. So this is at most root P times the Frobenius norm of A plus something that looks like A sigma prime L2 norm squared minus the expectation of A sigma prime L2 norm squared LP to the 1/2. Okay. And now what I can do is, again, apply decoupling. And I can say that this is at most up to a constant of 4, root P times the Frobenius norm plus, so decoupling says I can put here sigma transpose A sigma prime LP to the 1/2, right? And then, okay, so it looks like where am I going with this? It just looks like I'm back where I started, sort of, but we're almost there. And then I'm going to do ta-da Kinchin again. Okay, so this is at most by Kinchin, root P times the Frobenius norm plus now the L2 norm of A transpose A sigma prime. Okay. Now what I'm going to do is use the fact that this thing is, right?
Wait, should there be like a square root p or something?
Yes, you're right. There should be a root p right here.
Or actually like a p to the 1/4, right? Because don't you
Right.
have a,
I guess it should actually be, where did I do Kinshin? So I just did Kinshin here. And I was a little, there are root p's here and here too, right? There's a root p there.
yeah.
And then here it should be basically be p to the 3/4
Yeah.
because of Kinshin.
Yep.
Okay. So this is Kinshin. Okay, now we're like basically almost one line away. And then now what I'm going to do is I'm just going to say, look, like if I have, like a times b times x L2 norm, this is at most the operator norm of a times bx L2 norm, right? I mean, that's what operator norm means. Operator norm means like how much can you increase the L2 norm of the vector that you're operating on by. Okay. So then this is at most root p times the Frobenius norm of a plus p to the 3/4 operator norm of a to the 1/2 times we're a sigma prime. Oops, I'm getting too close to the bottom, I guess. A sigma prime L2 norm LP to the 1/2. Okay, does that make sense? So now I claim we're done, even though you might look at this and be a little scared. I claim we're done. Why are we done? We're done because let's just compare things. So we have this, somewhere along the way we had this. Let me actually go one level down. We had this thing that I circled in red. And we just bounded that by this. Okay, so why is that significant? Let's take this thing that I'm highlighting in yellow, and let's just call that let's call that E. Okay. So what have I just shown? I've just shown that is that what I? Oh, actually, let's go. No. Yeah, good. Yeah, good. So let me. I went a little bit too far down actually. So let's erase this red thing. This is what I wanted to say. This thing right here. This. Yes, that's what I want. So compare that red circle. I bounded that red circle thing by something on the bottom. So now let's call that thing that I circled in yellow E. What have I just shown? What's the thing in the red circle? It's actually just E squared, right? Right. The yellow circle is some norm of something raised to the 1/2, and that red circle is the same thing without the 1/2. So that thing is E squared. So what I've just shown is that root P times E squared is at most some constant times root P times Frobenius norm plus P to the 3/4 A to the 1/2 times E. In other words, what I've shown is that and I can cancel some root P's here and there, and you got, this is P to the 1/4 now. I've shown that E squared minus some constant times E minus some other constant is at most 0. That's what I've shown. So let's just plot that. This is some quadratic, right, where the x-axis is E, and the y-axis is this quadratic form, this quadratic equation or quadratic expression. And I know that in the limit as E goes to infinity, it goes toward infinity. So I mean, the picture looks something like this, right? That's the graph of E squared minus alpha E minus beta. And I'm telling you that I'm in a region where the quadratic is non-positive, which means that E has to be left of this point. It has to be somewhere here. Does that make sense? So I just got an upper bound on E, which is exactly what I wanted. Okay, I mean, now you just have to solve the quadratic equation and show that the root that you get is exactly the bound that you wanted. This is basically the larger root of the associated quadratic equation. So, I mean, that's essentially it. So maybe I'm not going to do that in lecture because I think it's a waste of time. There's nothing interesting beyond this point. It's really just solve a quadratic equation. Now you know that E is smaller than the larger root. That implies exactly the bound that you wanted for Hansen-Wright. Okay. So I know that was a lot of math on one board, but any questions about this? Or are people too scared to ask a question? Okay.
Is it also possible to get control like the p moments for p between 1 and 2?
Yeah, so yes, but you know that's kind of trivial because, as I said here,
Oh, because you have the less than, like the, yeah.
this thing, right? So now I can just bound the 1 norm by the 2 norm, for example. Okay.
And is that the right answer for this quadratic form?
No, it is the right answer if sigma had been Gaussian. If sigma's, so, okay, so why can't, actually that's a good question. Let's even go back here to Kinchin. Is this the right answer for Kinchin? No, it cannot be the right answer. Why can it not, why is it definitely not the right answer? Notice that sigma dot x is at most the L1 norm of x with probability like 1, right?
Mm-hmm.
Because again, the sigma i's are at most 1 in magnitude. They're either 1. So meanwhile, on the left, the p norm bound is going to infinity as p goes to infinity.
Yeah.
So it cannot possibly be correct for all p. This is now a random aside. It's known what the right answer is. The right answer is that for all p, if you look at sigma dot x p norm, for all p at least 1, this is equal up to a constant factor to the sum I goes from 1 to k, or p actually, of x star I, absolute value, plus root p times the sum I goes from p plus 1 to n of x star I squared, square root. So now this is the same thing as basically x head p. I'll say what x star means in a second. X head p L1 norm plus root p times x tail p L2 norm. So x star just means you sort x by magnitude in decreasing order. So like x star 1 is the biggest entry in magnitude in x star 2 is the second biggest entry, etc. So, I mean, the fact that this is an upper bound is easy, right? Just by triangle inequality. I can say I have sum of sigma I xi. Let me do triangle inequality to move out the largest p entries, and then I'll use Kinchin on the rest, right? And then for the part that I moved out the largest entries, I'll just use the trivial bound that it's at most the L1 norm. Okay. The fact that it's a lower bound requires more work, but it's been known by probabilists. I think the first person to prove it was someone named Montgomery Smith. But yes, the Kinchin is exactly correct for Gaussians. For plus minus 1s, it can't possibly be correct because you know that the p norm should not go to infinity. But yes, we know what the right answer is. Similarly,
So the basic issue is that you just have bounded random variables, or?
Yeah, I mean, in general though, even for like, I mean, if you have something that, all you know about sigma here is that all we're using in Kinchin is that it's sub-Gaussian, right? But I mean, sub-Gaussian means decays at least as fast as a Gaussian. But there's no reason to believe that Kinchin should be correct upper and lower bound for an arbitrary sub-Gaussian, right? I mean, just because you decay at least as fast as a Gaussian doesn't mean you decay exactly like a Gaussian decays, right? I mean, sigma I doesn't decay exactly like a Gaussian decays. What's the probability that sigma I is bigger than 2? It's 0, right? So there's no reason that you should expect Kinchin to be the right answer, right? Similarly with Hansen-Wright, it is the right answer. It's known. It is the right answer for Gaussians. For plus minus ones, it's not the right answer for a similar reason, right? I mean, the sum of aij sigma I sigma j cannot possibly be bigger than the entry-wise L1 norm of A.
Right.
Meanwhile, Hansen-Wright goes to infinity, but it's known what the right answer is. And if you want to look it up for yourself, there's a paper that has the right answer. It's due to Latawa.
When you say right answer, do you mean like tightest asymptotic tail bound?
Yeah, I mean that not only is it an upper bound, but it's a lower bound. Like up to it's the right answer up to a constant factor. So like I want to bound blah such that the p norm is at most c times blah and it's at least c prime times blah. So basically it's theta blah, right? So what I've been showing so far is just big O. I've been showing that the p norm is big O of something, whereas kind of right answer means theta of something. Yeah, so Latawa, that first, that L-A-T-A-L with a little thingy through it, some Polish letter, it sounds like a W-A. So he has a paper, I forgot the name of the paper. Well, actually, I can tell you right now.
And it's similar in that it just depends on the sorted values of A.
No, his is actually, unfortunately, a little bit more complicated. So his paper is called, I think, Tail and Moment Estimates for Some Types of Chaos. So yeah, probabilists, whenever they have polynomials and random variables, they call it chaos. Okay, so this is like Rademacher chaos. So when he's talking about moments of chaos and tail bounds for chaos, he means polynomials, and he's looking at degree 2 polynomials in that paper. But no, it's not. Unfortunately, it doesn't just depend on the L1, the entry-wise L1 norm of A. He defines some like restricted operator norm on A, where you take the I don't know. You just look at his paper. Unfortunately, it's not as simple as the other one. Okay, so I think let me not get too derailed. But yeah, that's Hansen-Wright. Okay, and this is the proof of Hansen-Wright I chose to show because it all fits. Once you have decoupling, it all fits on one board. It's not the most general proof because it's known that more generally, Hansen-Wright holds not just for plus minus ones, but for any distribution that's so-called sub-Gaussian, meaning that if sigma I decays at least as fast as the Gaussian does, you can basically get Hansen-Wright from that distribution as well. In the notes, I did have a reference to a paper of Rudelson and Verschinen in the probability review, which has the more powerful proof that shows it not just for plus minus ones, but shows it for sub-Gaussians. But for this entire semester in this course, we're never going to use this Hansen-Wright for anything other than plus minus ones, so not bothering with the more general version. Okay. Yes, so let's continue. So now you've seen a proof of Hansen-Wright. You can plug that into the proof of distributional JL, which you saw on Monday, which implies JL. So now you really have seen all details of a proof of JL. Okay. Oh, another nice thing I should mention, maybe before I move on to the last part of the lecture. If you remember, I said at some point, I think it was maybe last week, I was talking about like, if you have the Chernoff bound, and the Chernoff bound is giving you some failure probability of delta, in fact, the random variables didn't need to be fully independent. They only needed to be log 1 over delta y is independent. Remember I said that at some point? That fact is just like a corollary, essentially, of this yellow part of this board, right? Because, right, we know now tail bounds imply moment bounds imply tail bounds, right? And we saw exactly how to choose P, right? That was right when we highlighted in red. We chose P right here, right? So, right, if you have a tail bound, like Chernoff or Hansen-Wright or whatever, or Kinchin, okay, you know that you have a tail bound. That implies that you have a moment bound. But now that you have that moment bound again implies that you have a tail bound via Markov, where you know exactly which moment you're using for the tail. You're using P, in the case of Gaussian decay, you're using P equal to lambda squared over alpha squared. Okay. So, if you just kind of back solve and figure out what does that actually mean, It means, for example, in Chernoff, as well as Hansen-Wright, as well as Khinchin, that if you're shooting for a failure probability of delta at the end of the day, then P can basically just be log 1 over delta. Okay, which means that, you know, so a quadratic form is a degree 2 polynomial in the random variables. When you raise it to the pth power, you have a degree 2p random variable. The expectation of this degree 2p random variable is fully determined by 2p y's independence, which is 2 log 1 over delta y's independence. So you could have carried out your entire argument with your signs being 2 log 1 over delta y's independent. Okay. So for example, when we talk about the Johnson-Lindenstrauss lemma, we said, you know, we're gonna let our matrix pi have IID plus minus 1 entries. In fact, they don't need to, those entries of the matrix don't need to be independent plus minus 1s. They just need to be 2 log n y's independent. Why? Because when we applied VJL to get JL, we set delta to be 1 over n squared so that we could union bound over all the difference vectors. Log 1 over delta is now basically O of log n. So we just need O of log n y's independence. Okay. So we already now know that to get JL, it's enough that your random matrix only has log n, O of log n y's independent entries. Okay. Which means even though your matrix is big, it's M by D, you can be represented succinctly because the entire matrix is specified by a bounded independent hash function. Okay. Does that make sense? Any questions about that? I guess it's the kind of thing where maybe once you use it a few times, you'll get the hang of it and it'll be second nature. But what you should just keep it in mind that whenever you use one of these like exponential or Gaussian tail bounds, implicitly you only that the random variables that are involved only have to have bounded independence. They don't really actually need to be independent. Okay. Sorry, was someone about to say something before we move on to the next thing?
I guess I don't really see where the like log 1 over delta y's independence comes from, but.
Oh, okay. Yeah. So I didn't actually write any math down, but I guess what I'm saying is, so you're applying a tail bound. Maybe it's Chernoff, maybe it's Hansen-Wright, whatever, right? Your tail bound looks something like this, right? You know that for all lambda, your tail is bounded by some Gaussian thing or exponential thing or whatever. And we know that that implies that you have bounded moments, right? But now that you have bounded moments, we know that not only do you have a bounded tail, but to get that bounded tail, you're choosing a very specific moment to apply Markov on. Okay. Right. So like, so I mean, if you're looking at Chernoff, right? Chernoff is looking at the sum of xi minus mu. You want tail bounds on that. And I'm saying that that's the same thing as moment bounds. Moment bounds means the expectation of this to the pth power. Right. Yeah. So you can write that down as the sum of like xi1, xi2, whatever, mu to some power. And then you have expectations here, right? And the point is, this thing has at most p terms in it. So it's fully determined by py's independence. The xi's don't actually need to be fully independent. Usually when we state Chernoff, we say that the xi should be independent. They don't actually need to be independent. They just need to be py's independent, where p depends on the failure probability that you're getting at the end of the day. So if you're getting a failure probability of delta, and you basically unwind all of this, p right here is getting set to be something like log 1 over delta. That's what I'm saying.
Okay.
So maybe I'll let you marinate on that. But yeah, that's all I was aiming to say. So no, I didn't mean y's, I meant norms. So how can you estimate LP norms in data streams? We did p equals 2. That was like the AMS sketch or Johnson-Lindenstrauss. What about other LP norms? So definition, a distribution, let's say a distribution dp is p stable if for Z1 up to Zn IID from that distribution, and also like X in Rn is fixed. We have that, and let's also say we also have a Z. So Z1 up to Zn. Then what I want to say is that the sum of Xi, Zi is equal in distribution to the LP norm of X times Z. Does that make sense? So it's saying that if you sum up a bunch of p-stable random variables with different scale factors, what you get back is a p-stable random variable whose scale factor is the LP norm of the coefficients. So Gaussians, so p equals 2, Gaussians satisfy this, right? If you sum up a bunch of independent Gaussians, you get back a Gaussian whose variance is the sum of the variances. In other words, that Gaussian is scaled by the standard deviation, which is just the L2 norm of these coefficients. Okay. But it turns out theorem, such a DP exists if and only if 0 is less than p is less than or equal to 2. Okay. You can look up these things. So like, for example, p equals 1 is what's called the Cauchy distribution, which has a PDF that looks like phi of p of x is something like some normalizing constant times, I think, 1 over 1 plus x squared. That's the PDF. You can prove that this thing satisfies p stability. I think for like maybe all except this, for a few special cases, like p equals 2, p equals 1, and maybe p equals a half, there's no closed form for the probability density function of a p-stable random variable. You can just prove that the distribution exists. There is a closed form for the Fourier transform of the PDF. So, I mean, I'll just write that. You don't have to know what I'm talking about. But if you just take the Fourier transform of the PDF and evaluate it at a point t, it looks something like e to the minus absolute value of t raised to the p. And you're allowed to have a scale factor here. That scale factor could be arbitrary. And this is. Maybe there's some scale fact normalizing constant out here too, something like that. But actually, do you have the normalizing constant? Yeah, I'm not sure, but it looks something like this, right? And I mean, and the fact that this is p stable. I mean, so I guess yeah, what you always have is a closed form for the Fourier transform, but what you might not have is a closed form for the actual PDF. And the fact that something with this Fourier transform works is somewhat obvious, because what happens when you add independent random variables? Their PDFs convolve, which in Fourier land means their Fourier transforms multiply, which means that kind of, if you have e to the minus t alpha 1 to the p times e to the minus t to the p alpha 2, you know that, right? E to the a, e to the b, I'm just using is e to the a plus b. So in other words, if you have e to the minus t to the p times alpha 1 times e to the minus t to the p. Oh, there's no minus here, I think. Should there be a minus? I guess for Gaussians, there's no minus, right? I think maybe there's no minus. There's either a minus or not. Let's just say there isn't. Oh, let's say there is. I don't know. But I might have a typo there on us. I might have a sign error. Times alpha 2, right? This is equal to e to the minus t to the p alpha 1 plus alpha 2. Okay. So like that already gives you kind of a sense of why the Fourier transform, this is a good Fourier transform to have, because it says if you add two independent p-stable random variables, you get back a p-stable random variable. It's just that the scale factors, the scale factor changes. Okay, good. So, right. I guess what you really want to know is, well, okay, that's all I wanted to say about maybe p-stable random variables. Let's just use the fact that they exist and they can be efficiently sampled. So now how do you use that for estimating LP norms of data streams? So streaming, basically turnstile, we want a 1 plus epsilon approximation of the LP norm, which is defined to be the sum of xi to the p to the 1 over p with probability at least 2/3. So Indic in I think 2000 consider the following matrix pi. Each one of these entries is like Zij or Z, let's say ZRJ is p stable. Okay. So what you do, and you estimate the LP norm of X as the median entry of, you look at pi x I, absolute value. So like, let's say y is pi x, so this is just yi. So that was his algorithm. And properly normalized, so you normalize dp so that this is true. So dp looks like this, right? It's some distribution. I mean, it kind of looks like a Gaussian distribution. It's bell-shaped. It's just that the smaller you make p, the heavier tailed it gets, right? So Gaussians decay like e to the minus lambda squared. You can show that a p-stable random variable for p less than 2, it doesn't decay like e to the minus lambda squared. It decays like 1 over x to the p. Okay, or actually, the PDF. Let's see, the PDF is like 1 over x to the p plus 1, I think. Yeah, so the decay is like 1 over x to the p. And when I say normalize, so you're going to normalize it so that if you look at the interval from -1 to 1, this area is equal to 1/2. So in other words, if you take the expectation of the absolute value of a p-stable random variable, it's 1. I mean, that's just a matter of scaling, right? If you have a p-stable random variable and you just like scale it by some other constant, you still have a p-stable random variable. So what I'm saying is take your p-stable distribution and scale it so that this is true, so that the amount of area in between -1 and 1 is exactly 1/2. Okay, and then use that as dp, and then this is his algorithm. He maintains pi x in memory and he outputs the median as the final thing. So now the question is like, why does this work? So,
by the way, just a question. Yeah. Is there something interesting happening when p is equal to 2 or as p is getting closer to 2? Like, it seems weird that all of a sudden you get really fast tail decay when p is equal to 2, and then it slows down considerably as soon as you have 1 plus epsilon.
Right. So so one thing that's magic about p equals 2 is maybe you've heard of the central limit theorem, right? Which says if you sum a bunch of independent random variables, it starts looking like a Gaussian. Okay. Now, but there's a caveat. The central limit theorem only holds when the random variables you're adding have bounded variance, right?
Mm-hmm.
So you could say like, wait, how could a one stable distribution exist? Like central limit theorem says if you add a bunch of copies, it should look like a Gaussian. So like, shouldn't everything be like kind of too stable or something? But there's that catch of bounded variance, right? So except for p equals 2, none of these distributions have bounded variance. In fact, all of these have infinite p norm. So all p stable random variables other than p equals 2 have infinite p norms. They have infinite q norms for any q that's at least p. So in particular, like the one stable distribution, the Cauchy, doesn't even have finite expectation. It has infinite expectation. Okay.
Got it.
And then kind of once p starts getting bigger than 2, it's like, well, you can't have something 3 stable because now central limit, you can prove that if you're p stable, your tail decay has to be at least as fast as 1 over x to the p. So if you're 2.1 stable, you're decaying at least as fast as 1 over x squared to the 2.1, which means you have bounded variance. Yeah. But then central limit theorem applies, right? So you can't. So yeah, that's why 2 is kind of a magic number. Mm-hmm. So that's his algorithm, and now let's analyze his algorithm. So you're maintaining y, which is pi times x. Notice that like y is distributed like the LP norm of x times a p-stable random variable. So what we're saying is, like, if you look at the expectation of the indicator function of -1, 1 applied to y, let's say yr divided by the LP norm of x, this is a half, right? So, right, the indicator function of an interval is just, I'm saying 1 if x is in, applied to x is 1 if x is in the interval, and 0 otherwise. Does that make sense? I mean, this thing is the same thing as, I'm just rewriting in a fancy way the probability that yr over xp, oops, is in the interval from -1 to 1. Right? The expectation of the indicator of that interval is the same as the probability that you're in that interval. Okay. And since I scale the distribution so the median is 1, then I have exactly this. Now, what does the distribution look like? I mean, take my word, it looks like this. And, you know, here's -1 and here's 1. What if I went to 1 plus epsilon? And what if I went to, you know, like 1 minus epsilon? So, question for you: how much mass is in that? How much mass is in that yellow region? Like, what can you tell me about that? Not, don't give me an exact number, but rough estimate. How much mass is in the yellow region? Probability mass. Right? It's theta of epsilon, right? Because it's basically upper bounded and lower bounded by different rectangles. And these rectangles have some heights that, you know, those heights are some constants that depend on the distribution, but there's some fixed number. And the width of this rectangle is epsilon. So this area is like theta epsilon. And, you know, that other red area is also theta epsilon. Okay. So now what I'm going to do is the following. I'm going to look at the sum. R goes from 1 to m. Let's say 1 over m. The indicator function of -1 minus epsilon, 1 plus epsilon, yr over xp, this thing. So, okay, so what is this mouthful actually computing? It's computing what fraction of, so I'm maintaining y, which is pi x. So y has r different entries, right? M different entries, right? So y is like an m-dimensional vector, right? Because pi has m rows. So it's like, what fraction of these m entries? So I'm counting like what fraction of the m entries of y satisfy the absolute value of yr is at most basically 1 plus epsilon times the LP norm of x, right? That's what this thing means. Does that make sense? And let me ask you, what's the expectation of this? Right? I'm basically saying I'm moving a little bit into that red region. I'm widening the interval. Instead of -1 to 1, I'm going -1 minus epsilon up to 1 plus epsilon. So I'm gaining a little bit more probability mass, namely that red probability mass. So this, by linearity expectation, is a half plus theta epsilon. Does that make sense? Similarly, if I look at the expectation of 1 over m, sum r goes from 1 to m, indicator of -1 plus epsilon, 1 minus epsilon of yr over LP norm. This is a half minus theta epsilon. And this is basically saying what fraction have...
Wait, the diagram that you have written, that you've drawn, is different than the one that you're taking the expectation of, right?
No, I think it's the same, right?
Well,
The-
you
the-
have, I think it should be an interval to the left of -1, right?
well, no, okay, so
Because it
I
says
mean, but
-1 minus
I'm doing it on
epsilon.
both. I'm doing it on both sides, right? So this is -1. Oops. This is -1 minus epsilon, and this is like -1 plus epsilon. So I'm gaining like the
You're
two
gaining
red
like
regions.
epsilon on both sides, right?
Yeah, but theta epsilon plus theta epsilon is theta epsilon.
Yeah.
So like, So in the first equality, I'm gaining the two red regions. In the second equality, I'm losing the two yellow regions. Okay. So let's imagine that this is not just happening in expectation, but this is like actually happening. So what am I saying? I'm saying that more than half of the entries are less than 1 plus epsilon times the LP norm, and less than half of the entries are less than 1 minus epsilon times the LP norm, which must mean that the median entry is between 1 minus epsilon and 1 plus epsilon times the LP norm, which is exactly what I want, right? The median is my estimator. Does that make sense? So if both of these things actually happened and didn't just happen in expectation, I'd be very happy. So now I want to argue that it's not just happening in expectation, but it's actually happening with good probability. We're going to use our usual trick, which is Chebyshev's inequality. Or, like, if it helps, let me get rid of the 1 over m here and move it outside. So this is basically m over 2. This is basically m over 2 plus theta epsilon m, and this is m over 2 minus theta epsilon m. So what I'm interested in is something that looks like, the variance of the sum of the indicator, blah, 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 of like YR over XP. Okay. Now the variance of independent random variables, like when you have independent random variables and you sum them, the variances add. So what is the variance? Give me an upper bound on the variance of one individual indicator function. The most trivial upper bound you can give me.
1/4.
I mean,
Yeah, 1, right? The indicator function is always between 0 and 1, so the variance can't possibly be more than 1. That's like the absolute most trivial bound you can give me. So I'm just going to say that this variance is at most m. So by Chebyshev's inequality, Chebyshev basically says that you're usually within a standard deviation of your mean, right? That's what it says in words. So by Chebyshev's inequality, this is usually this plus or minus O of root m. And this is also plus or minus O of root m. And I want to make sure that this O of root m error from the standard deviation is not canceling the epsilon m. So basically what I want to make sure is I want to make sure that this root m factor is like much less than epsilon m, which is the same thing as saying I want m to be like at least 1 over epsilon squared. And that's it. I'm done. Does that make sense? Right. So we've just shown that as long as you have 1 over epsilon squared rows in this matrix, you succeed with probability 9/10. That's implied by Chebyshev. Okay. Now, how do you de-randomize this? This is a giant random matrix. It seems kind of hard because we're very much, in these two locations right here, we're very much using independence of the entries in the matrix, because we're saying if you sum up a bunch of independent copies of a p-stable random variable, you get back a p-stable random variable. That's not true necessarily with some pseudo-random version of the p-stable random variable. And so we're also using it here to say that the variance of a sum is equal to the sum of the variances. But that part is easy, right? Variance of the sum equals sum of variances. That only requires 2-wise independence. So what we can say is, look, we could, there's some random seed that's being used to generate each row of the matrix. We can just make sure that those seeds are only from a pairwise independent family, okay? So, each seed, if you look at each seed individually, that seed is generating a uniform row, like uniformly, independently random. But the seeds from row to row are actually only 2-wise independent. Okay, so we've already made some progress. The next thing that we would want to show is to show that if the basically we want something like this. We want something like this to still be true, even if the p-stable random variables are not fully independent, but almost fully independent. They're like k-wise independent. And that is true. So theorem, if the zi are k-wise independent for k being at least like 1 over epsilon to the p, then for all intervals let's say intervals ab, let's say for all ab, if you look at the expectation of the indicator function of ab, let's say zi primes are k-wise independent, and you look at the sum of zi prime xi, this is equal to the expectation of the indicator AB of the sum of the zi xi up to an additive like epsilon term, epsilon added epsilon, where these are actually IID. So this is a theorem about like the approximate p stability. It says that if your p-stable random variables are only k-wise independent and not fully independent, then the CD, notice that like the indicator function of minus infinity a, this is just called like the CDF, right? The cumulative density function or distribution function. So what this is really saying is, if you have k-wise independent p-stable random variables instead of fully independent p-stable random variables, the CDF of sum of zi prime xi almost looks like what it should look like. At every point, the CDF will be correct up to an additive epsilon error. So this is a theorem that was proven by Daniel Kane, myself, and David Woodruff in 2010. So I'm not going to prove that. Unfortunately, that is actually pretty complicated. But in the last couple minutes, I do want to talk about this general hammer of like, when Indyk wrote his paper, it was not 2010 yet, it was 2000, it was 10 years before. So how did he de-randomize his algorithm? He used something called Nissan pseudorandom generator. And the idea there is you can define what's called a branching program. This is some model of computation that's supposed to represent like space-bounded computation. The idea is you have like a start state. And then, you see the first input. Let's say that your inputs are bits, but they could, they don't have to be bits. They can be from any alphabet. You see a 0 or you see a 1. That's going to change the state of your algorithm. You're going to enter a new memory state based on what you see. And then from here, you see a 0, you see a 1, and there could be overlap. So here you see a 0, 1, here you see a 0, 1. And there's basically like a layer over time. So let's say this is time, where you're seeing inputs one by one. And you just basically have this kind of graph where every node has out degree 2. Does that make sense? And then this is kind of the final time step, where this is your final memory configuration after processing the entire input. How is P being used here? Where are you? So Noah, you're asking about P. P. So yeah, the ZI prime are P stable. So P is the stability parameter. If that answers your question.
Yeah.
Okay, so you can imagine that at every time step, I'm seeing either a 0 or 1, a 0 or a 1, a 0 over 1. Imagine 0 or 1. And what you should imagine is that kind of this input, this 0, 1 input, is like the specification of the hash function. First I'm telling you what h of 1 is. Then I'm telling you what h of 2 is. Then I'm telling you what h of 3 is. I'm revealing h bit by bit. Okay. And then I'm saying like now after I've revealed all of h, that implies some kind of probability distribution over your final memory state, right? Now, if those 0, 1s had actually been independent, there's some distribution that you would have on your final memory state. And now I could say, what if the 0, 1s are not actually independent, but they're generated by an algorithm, a pseudo-random generator like k-wise independence or some other method? Is your distribution over final states still approximately the same? Because if it's still approximately the same, that means that if you used to be correct with probability 2/3 before, you'll still be correct with probability approximately 2/3 now, right? So that's what I want. I want to generate these red bits in a way that keeps your final memory state distribution similar. Okay. So does that make sense? That's the name of the game. Now, if you look at here, the kind of the number of, let's say, nodes per layer is called the width of the branching program. And this is basically 2 to the s, where like s is the memory, right? Because if you have s bits of memory, you have 2 to the s possible memory configurations you could be in. Right? Okay. So so now what? So now theorem. And this is due to Noam Nissan in 1992, that if the branching program has, and by the way, this is called read once branching programs, because you're never allowed to like go back in time and read a previous input. You have to read the inputs in this kind of streaming fashion. So if you have a read once branching program that has, let's say, L layers and with 2 to the s, then there is an algorithm, let's call it A Nissan. It's called a pseudo-random generator. And let's call this branching program, let's call this P for program. Pseudo-random generator. Such that if you look at, and in his model, the out degree is 2 to the s at every layer. So he's imagining that you're not just reading 1 bit at a time, but you're reading s bits at a time. Okay. So since you're reading s bits at a time, there are 2 to the s out arrows depending on what you just read. Such that if you look at the distribution, so apply P to the uniform distribution on L, let's call it LS bits, right? There are L layers, going from layer to layer, there are S bits that you're seeing at a time. So just imagine you have the uniform distribution on L times S bits, okay? And then you apply P. P is this branching program. You can think of P as computing something, namely, it's computing what its final state, memory state will be. So P of a string is just what's the final memory state of P when you run it on that string. So P on a uniformly random string is a probability distribution over final states. So you look at this distribution versus P applied to Nissan on a uniform distribution on let's say, qubits. So now you generate Q random bits, you feed that into Nissan. Nissan will spit out LS bits, you feed that into P. These distributions are close. Where Q is O of S times log L. So I think I'm basically out of time. But what this is saying is that you have some low memory algorithm which you're going to model as a branching program. Okay, that's your branching program P. Maybe I'm gonna release the homework very soon. Maybe I'm gonna do this. I'm gonna make you do this for index algorithm and de-randomize it using this theorem. Give you some practice with it. But you have a low memory algorithm P, and I say, what if I fed P uniform random bits? I'll have some distribution on its final memory state. And then you say, okay, I'm not going to feed it uniformly random bits. Instead of taking LS random bits, LS is very big. Think of L is huge, let's say. So instead of ls random bits, which is a huge number of random bits, I'm only going to take q random bits, where q is only log L. It's not L, it's log L. So it's much fewer. A Nissan you can think of as like a function that takes q random bits and spits out ls random bits. Okay, those ls bits cannot possibly be uniformly random because you took few bits and you stretched them out into more bits. There's no way those things are independently random. But from the perspective of P, it looks random. So the distributions between PULS and PA Nissan UQ are close in L1. And if you're not familiar with this, close in L1 basically means that there's no, if you're epsilon close in L1, it means that there is no way to distinguish the distributions with distinguishing probability better than epsilon. So that means that if your success probability used to be 2/3, your success probability is still 2/3 up to an additive epsilon. So now here epsilon is 1/2 to the s. So your success probability used to be 2/3. Now it's still 2/3 up to an additive error of 1/2 to the s. Okay, so that's Nissan's theorem, and you're gonna have practice applying it in to index algorithm on the homework. So final questions. I know I went over time by 5 minutes.